All right. So the next two lectures will be about design of combinational logic. So there will be combinational logic design 1, and then of course we will have a combinational logic design part 2. So in part 1, we will be focusing on combinational components such as decoders, encoders, and also tri-state buffers. And in part 2, we will focus on multiplexers, adders, multipliers, and so on. So what is combinational logic and what are we designing for? So we are designing, essentially what that means is we should be able to put these components together in order to achieve a certain design objective. And the components that we are looking at are falling under the category of combinational logic, meaning they do not have any memory. The outputs in these components depends on the combination of present inputs. There's no memory involved. Now, in order to understand and document our design procedure, we have a set of documentation standards. Now, I'm not going to bore you guys with all the details because this can be a little bit of a dry discussion. So I'm going to go through this very briefly. So the first thing that you would need to look at whenever you're trying to do a design is to draw a schematic diagram. Now, this could be on paper or this could be using some CAD tool. The CAD tool that we'll be looking at later in the class is LogicWorks, in which you can drag and drop symbols of logic gates and even of integrated circuits, and then you can connect them using wires to achieve a certain design. Or you could also use that for analysis of a given design. So schematic diagrams, what are these? Like this will have what? Logic diagrams. And this will have essentially symbols and wires. You have been seeing many schematic diagrams from probably day 2 of this class. But those would be falling in that category of documentation standards. Next would be timing diagrams. Something similar to what you sketched in the exam. So what is this? Time sketch. So the x-axis of your diagram is time, in which you sketch inputs and outputs, both with respect to time. Now, an interesting question over here is, if I say that a schematic diagram completely represents a logic function, you might say, all right, fine, yeah, I can see that. If you have drawn a particular logic diagram, then it might represent the complete logic function. So for example, over here, we can go back and take a look at one such example right here, say, right? This is a logic diagram. So if I give you this, then you can come up with its truth table, you can simplify it, you can synthesize it, it uniquely describes, it doesn't uniquely describe, but it describes the logic function completely. You don't need any more information. You know that there are 3 inputs, 1 output, and you know how the inputs and outputs output is related. Now, can I say the same thing with respect to timing diagram? So the question here is, can a timing diagram completely capture a logic function? What do you guys say? The answers, possibility of course, are yes or no. Not really, no, yes. So not really. All right, so everybody is saying yes or no, but I really like the answer, the first one, not really question mark. Because it can only be yes. This happens only when the timing diagram has all input combinations. Otherwise, it's going to be a no. Right. So only in a particular situation it is yes. Now, when you guys get your exam 1 grades back, you can go back and take a look at that timing diagram question that was asked, and you can observe I had 3 inputs, 1 output. A, B, C were my 3 inputs. So does that timing diagram completely capture the function which it was referring to? And you will see that the way I arranged A, B, and C was that it goes from 0, 0, 0 all the way to 1, 1, 1. Bait is right. Yes, it does in that case, because I had covered all possible input combinations in that timing diagram. If I leave out some, then it doesn't capture the logic function completely. So the answer to this question is yes, but only when all input combinations are captured or are represented in the timing diagram. All right, next documentation standard is your hardware description language. In short, we call it HDL. And the two popular hardware description languages are VHDL and Verilog. And VHDL is what you guys have been using for your studios. Verilog is another such hardware description language. There are pros and cons between VHDL and Verilog. In my experience, what I've seen is VHDL is a very good place to start writing code for hardware description language. It's easier to understand, it's easier to teach, it's easier to follow, it's easier to troubleshoot. Verilog, if you guys get some expertise in VHDL, then you can move on to Verilog if you're interested. But those are the two popular ones. All right, let's move on. So that 3 documentation standards. Now, in terms of schematic diagrams, there can be a lot of information that could appear on the schematic diagrams. And that can include details of components, reference designators, the pin numbers, an optional title block, names for all signals. And then if your design is going to multiple pages, then you need to have page-to-page connectors. So let us take a look at an example schematic diagram and try to identify where are the pin numbers, where are the reference designators, and so on. So an example schematic is shown over here, and it has a bunch of NOT gates and NAND gates. So I have 2 NOT gates over here and 1, 2, 3, 4, 5, 6. 6 2-input NAND gates, right? So each gate has a part number. So part number appears at the top of the gate. It is belonging to the 7400 series ICs, 74HCT, high-speed CMOS technology 00. So 7400, those are the 4 numbers over there, that essentially corresponds to quad 2-input NAND gates. So 7400, that's an IC in which there are 4 quad 2-input NAND gates. You of course don't have to remember this, but that's what the number suggests, 7400. And then The HCT is essentially the technology that is being used by the manufacturer to design that IC. So HCT, high-speed CMOS, LS, low-power Schottky. So there can be other variations as well. Now for NOT gates, the number is 7404 and HCT for the technology. So there are two NOT gates over here. Now, when you see the NAND gates, the part number is kind of very obvious here, but I hope you see that they have a designator as well, right? There is a reference designator associated with each of those symbols. Where is the designator? It's right here. U1, 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 and then there is a U2, U2. Why is there a U1, 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 U1 4 times? Because that particular IC has 4 of these NAND gates. So I'm going to use the same reference designator for the 4 NOT gates. So essentially that means that these 4 NAND gates are belonging to the same IC. Let me number them. 1, 2, 3, 4. And then the 5th and the 6th one are belonging to the second chip. So that's why you have U2 over there. Similarly, 7404, that's a hex inverter. So there can be 6 of these inverters inside one IC. For that, the reference designator U3 is being used. What are the inputs? The inputs are being labeled here as ABC. What are the outputs? There are 2 outputs here in X and Y. The outputs are related to the inputs using the logic function that is represented by the schematic. And to help us design this, we also have the intermediate signals. B underscore L, A underscore L, and so on. Now the underscore L essentially means that is a signal that is active low. Do not understand why 4 of them are called U1 and the last 2 are called U2, because you see all these 4 are in one IC. All right, let me group them. All of these are in one integrated circuit. So if we think of a chip like this, the 4 NAND gates were inside one chip. And then the other 2 were in the second chip. So that's why we used U2 for that. Does the choice of which circuit matter? Why not make all the first level logic gates in one chip? Oh, no, it doesn't matter. No. It's just a matter of convenience. It's just a matter of it's just a matter of when Jeff has put up a data sheet for the 7400 number. It doesn't matter which one. All that you need to care about is U1. Why U1? Because they're all going into one IC and the next 2 are going in the second IC. It doesn't matter. All you need is a 2 input NAND gate. Which IC you take it from doesn't really matter. You could have used 6 different ICs, but then that's not a very efficient use of your ICs, is it? So we have talked about details of the components. Oh, pin numbers, right? So pin numbers, you see, let's talk about pin numbers. Let's highlight them in black. Now, because I have used U1 for these 4 2 input NAND gates, I've used pin 1, 2, and 3 of that IC for the first one, 4, 5, and 6 for the second one, 8, 9, and 10 for the fourth one, and 11, 12, 13 for the last 2 input NAND gate. What I have left out in this case is pin number 7 and pin number 14. So pin number 7 is reserved for a ground connection of the IC, and pin number 14 is reserved for VCC, say plus 5 volts power supply. All the other pins have been used for input or output of the 2 input NAND gates. Is this an optimized schematic? No, this is just an example schematic. So it is just an example of a certain function which has a couple of NOT gates and a bunch of NAND gates. So we have talked about pin numbers, we have talked about part numbers, we have talked about reference designators. So the 7400 has a max number of 4 NAND gates. Yes, only the 7400. Now, there is a complete list of NAND 7400 series ICs, right? So we have just looked at the first one here. There are many 7400 series ICs. These are dual inline package ICs that have been here, that have been present in the market for many decades. And each one may have 4 or may have 6. In the case of 7400, it's a hex inverter, so 6 inverters in there. Triple 7410 has a triple 3 input NAND gate. So it depends really on the limitation of the number of pins and the number of inputs a user may need. So you have a case where you have 2 inputs, 3 inputs, and also 4 input maybe also be there, but that number might have not made the list here. But the complete list is on Wikipedia. Let's see. And you don't have to remember these. This is just for your reference. If you want to design, then you need to be aware of what all, yes, IC means integrated circuit, yes. And if you are trying to design for a certain logic function, then you need to be aware of all the ICs that are available to you that you can use in your design. All right, let's go back here and take a look at this. So we have talked about inputs, output, interconnections. We have talked about designated title block. All right, so where does title block go? Usually a title block is at the bottom right of the circuit, and it is used to list out who was the designer, what company, what date was this designed, how many pages are there in the design, what is the title of the design, all those details, which version of the design is this, all those details go in the title block, usually at the bottom right of the schematic page. Page-to-page connector. So when you have a very complicated design, then you might need to break it down into maybe a flat structure or a hierarchical structure. In that case, you will need a page-to-page connectors. We'll take a look at an example in just a minute. All right, did I miss a question at the beginning here? So is this specific case, there are 3 individual chips? Yes, Arham, there are 3 individual chips. 2 7400s and 1 7404. Can we go over signal names again? Yeah, so I will focus on this, right? So let me show you this. This guy is A, right? And then it goes through a NOT gate and it becomes A underscore L. Now, why is that chosen, A underscore L? Why not some other name? Well, you could have chosen any other name, but we want those names to mean something to us. So A, when you do not see any underscore L, for example, that means that A is a active high signal. It is active when it is high. And A underscore L essentially means it's an active low signal. So the name of the intermediate signal is written in such a way that it conveys some information to the person who is looking at your schematic. So if you see underscore L at the end of the name, that signifies that that particular signal is active low. What does that mean? It means that the signal is active when it is low. More about active high and active low in a few minutes. And then similarly, you have the 4 active low intermediate outputs of the 4 NAND gates over here, and then you have the final outputs in X and Y. Let's move on. Let's talk about the packages in which these ICs come in. So these are dual inline packages. There could be many versions. 14 pin is the most common. You could also have a 20 pin or a 28 pin IC. These are not surface mount. As you can see, these are through hole components. They go into the IC and you solder them on the back side. What information can you get from here apart from showing the size, the size, right? The distance between each pin is talked about and all that. But what you really need to know as a user of these ICs is, where is pin 1? Pin 1, so usually there will be a notch, and then followed by a black dot when you are looking at the IC from the top. And that particular pin, that particular dot is actually the pin 1 indicator. And even if you don't have the dot, if you just have the notch, then you read the numbers counterclockwise. So 1, 2, 3, 4, 5, 6, 7, and then 8 through 14. And as we said, pin number 7 here, this guy is 7. That should be connected to ground. And then pin 14 is top right. That is usually connected to a plus 5 volts power supply. Once you connect the chip to ground and power supply, then you can use all the other pins for inputs and outputs. You can use that for the purpose you want them to be used as, right? So for example, if you wanted to use pin 1, 2 as the inputs of the NAND gate and then observe the output on pin 3, it is understood that you have already made the connection of power and ground to the chip, and then you are using 1, 2, and 3 here. Right. So without the power and ground, the chip is not going to function. All right. And then there could be 20 pin ICs. There could be 28 pin ICs, depending on which pin you are looking at. The most common is the pin 14 pin IC. Now, if you had X-ray vision, and if you looked at, well, you will not look at, even if you had X-ray vision, you would not observe symbols inside the IC. You would actually look at all transistors. But if you were to look inside the IC for symbols, then this is what you would see inside each IC. So let us take a look at 7400. We have already used it for one of the example schematics before. That's your notch that indicates that this is going to be pin 1, and then you're going to read counterclockwise all the way to 14. Inside the IC, what do you have? You have pin 1 and 2 as inputs to the NAND gate. Pin 3 is the output. And then similarly for 4, 5 inputs, 6 is the output, 7 for ground, 14 for VCC, 13, 12 inputs, 11 is the output. And similarly 10, 9 is the input, 8 is the output. So you've got 4 2 input NAND gates in that particular IC, 74X00. In the same manner, you could have ICs that could have quad 2 input NOR gate, hex inverters, quad 2 input AND gates, 1, 2, 3, triple 3 input NAND gates, and so on. As you can see, 7430, it actually has an 8 input NAND gates as well. So these ICs are available in the market, and depending on what your design requires, you would use them. Are pins 7 and 14 always reserved for ground and power supply? Yes. Do you have to do something? Do you have to have something plugged in to every input, or can you have some open? Yeah, you can always have something open. So for example, if my design only needed one 2-input NAND gate, I would just use this, right? I don't need to use all the others, but I still have to give the IC power and ground, and I can leave all the other pins open. Don't need them. All right, let's go ahead. Now, this slide is kind of repetition of what we saw earlier. The only difference is that now the symbols of the gates inside the IC are drawn as individual symbols with the pinouts, right? So for 7400, we know that it is 4 2-input NAND gates, and you can see pin 1, 2, 3, 4, 5, 6, 9, 10, 8, 12, 13, 11, 7 and 14 for ground and VCC. Similarly, all the other gates are also shown. So for example, 7414 is a hex Schmidt trigger based inverter, right? I hope you see the symbol inside, right? I hope you see that this particular symbol inside. Can you reverse the pin inputs and outputs? No, you can't. So the outputs have to be used as outputs, and the inputs will have to be used as inputs. We cannot change them because these are like physical ICs. These have already been manufactured, so their functionality is set. All right, let's talk about two symbols that are probably new at this time. One is over here. That's the symbol of Schmidt trigger behavior. Schmidt trigger. And the other one is for open collector. The one that you see over here. That symbol is for open collector. So open collector essentially means that the collector terminal of the transistors here are either connected to ground, or you can connect them to ground, or if you don't, then they are in high impedance. They are left open. They are not connected to anything. The collector is a dangling wire. So that's how those ICs are made. Now let's get into the Schmidt trigger behavior. What does Schmidt trigger mean? Some of you might have heard this term Schmidt trigger in your other classes, and if so, you can share what you learned. What I'm going to do is I'm essentially going to take an input and output, and then I'm going to talk about Schmidt trigger behavior here. So suppose you have a Schmidt trigger inverter, right? So this is, I'm going to draw the symbol here first. Come on. I have a NOT gate, and inside the NOT gate I have that particular symbol. So that's my Schmidt trigger based inverter. So for this, I'm going to say my input is in, say, A, and my output is A complement. And let me draw the output in blue, and I can leave the input in red. So for input, let me draw some input, some arbitrary input. I can say, all right, my input is something like that, right? And my x-axis is time. My y-axis is the amplitude. of the input or the output. Now, if A, that's red, right? That's the input. If I give that to the Schmidt trigger based inverter, my goal with this exercise is to sketch the output of this logic gate. But it has to be based off of Schmidt trigger behavior. Schmidt trigger behavior first starts with two thresholds. There's an upper threshold and there is a lower threshold. So I'm going to draw two horizontal lines that indicate the upper threshold over there and say the lower threshold is somewhere here. So now what that means is the output is only going to be sensitive to the crossing of those two thresholds. It is not going to it's not going to mind any change in between the two thresholds. So let's start over here in blue. All right. So at this point, I can see my input going above the upper threshold. So if the input is going above the upper threshold, that's when my output goes low. So that let us think of that as a low output. And before that, I'm just going to assume that it was high before that. Now, it will remain low until the input doesn't go below the lower threshold. So where does it go below the lower threshold? Right there. Right. So until that time, the output is going to remain low. And then once the input goes below the lower threshold, the output jumps high. Notice that this is an inverter. So it is going to be doing the opposite of the input, right? So if the input goes low, the output is going high because it's an inverter. But the trick over here is that it is responding to two thresholds as opposed to a normal inverter that only responds to one threshold. Now, what is required next? It is going to remain high until the input goes above the upper threshold, which happens here. So it will stay there, and then maybe at this point it will drop down. Maybe I need to move this a little bit to the right. Okay. Stay there until this happens. And then at that time it will go up again because the input went below the lower threshold. Let me identify these points. This is the high level here. This is the low level there. This is the upper threshold, actually upper threshold level, and then lower threshold level. Would we assume that this is the same behavior as PMOS transistor? Oh, so this is for the complete NOT gate, right? So this is for the Schmidt trigger based inverter. So this will have CMOS transistors, right? So it will have PMOS and CMOS, NMOS and PMOS transistors that go inside this. But the way this is designed is such that it responds to two different thresholds as opposed to responding to one threshold. Now, so once you see this, what is really important here is, why do you think this is useful? Why not just have one threshold? Why have two thresholds? What is this how is this beneficial? Noise. You're very close. So I wouldn't say noise margin, I would say noise, right? The immunity to noise. Now, if I were to ask you guys, think of noise in general. In general, where is noise? What is the mean of noise? The most general sense of noise. What is its average? 0 is right. So most noise behaviors will be the mean, the average of that noise will be 0. It will be going above and below 0, right? So if suppose you had noise on the input itself. So for example, what I can do is maybe over here I can erase some part of my input and draw this. You see, I'm trying to represent some noise behavior over here. What did my inverter do? It did not respond to that. It did not take that into account. It just ignored all of this noise. But if I had a NOT gate that was responding to every low and high change with one threshold of say 0, then my input would have been going 0, 1, up, down, up, down, up, down as the input is crossing the 0, right? So due to noise, I might have a lot of accidental fluctuation in my output, which I have just removed by responding to 2 thresholds as opposed to 1 threshold. So that's essentially the usefulness of Schmidt trigger behavior. All right, so I hope that you guys found that helpful. That's what this means, right? Like, so whenever you see the symbol inside a logic gate symbol, if you see that particular Schmidt trigger, that 2 thresholds being sketched, you know that those are the upper threshold and lower threshold, and by nature that is going to have a better response to noise. All right, let's move on here. All right, so here, coming back to this list of all 7400 series ICs, and depending on what you need. So for example, if you need Schmidt trigger inverters, what will you look at? You will look at 7414. That's what you have over there. Hex. So you have 6 of them in one IC, 7414. Would the upper threshold level and the lower threshold level be generally close to 0 or closer to the higher value? So it depends on what you design it for. So actually, maybe in your circuits related classes, you can you will see that using an op amp, and by changing the resistors that you connect around that op amp, you can actually change the upper threshold and the lower threshold. For 7414, if you look at the data sheet for the IC, those will be fixed. Those will not change because the IC has been already manufactured. But the fact that it is close to 0 or away from 0, that if you're designing for that, then you will have to take a bunch of things into consideration. And it matters a lot about how much noise do you have, how much noise do you want to tolerate, how much noise do you want to ignore, and how much noise you don't want to ignore, right? So you can design for that. You can change your resistors values around the op amps to change to have a different upper threshold and lower threshold. They don't have to be even the same. Like for example, +1 and -1, they can be different on either side. All right, let's move on here. All right, let's come to the topic of flat schematic structure and the hierarchical structure. So if you have, say, 6 pages are being shown over here, but what is interesting is in each page, there are not too many things. So if your design itself is simple, then a flat schematic structure in which each page is at the highest level is okay, is going to work, because it's not much to go through, right? It's not complicated enough. But what is the problem of the flat schematic structure as the complexity of, what do you mean the highest level? So what I mean is at one level, right? So think of a pyramid. If I think of a pyramid, I say, all right, I will have smaller designs at the bottom and I will group them into a fewer bigger blocks. And then as I go to the top, I will have only one file that I will call top level. This particular term, top level, should ring a bell, right? So you have used that in Studio 3 and Studio 4. When did we use that? Because that particular file was created when we were putting everything together. So all the things that we had under top level were lower in the pyramid, and only one file was at the very top. Now, that is a hierarchical structure where you are building complexity as you go up. You are trying to put one thing into the other, right? Layers of abstraction. But with flat schematic structure, everything is at one level, no matter what level it is, highest or lowest, everything is at one level, right? So that's what I mean. Richard says too many pages, organization. Okay, so that could be a problem, right? So too many pages, readability and troubleshooting, that can take a hit as my design gets more and more complex. So a better strategy for complex designs is a hierarchical schematic structure, which is shown over here, where page 1 has top level design, where you essentially have blocks, but the details of what is inside the block is not shown on page 1. It is shown on page 2 perhaps. And in page 3 you have some other module which also has certain blocks which are broken down later on, right? So you have a hierarchical structure over here which is easily readable, and if you have problems that you need to troubleshoot, this is much easier to handle as opposed to a flat structure, because a problem happens there, then you're going through all the 6 pages. Where is the problem? But if a problem happens here, then you are just going down that particular line of pages. All right, so I hope that you found that helpful. This is an example of a top level diagram. I could have easily put your Studio 3 block diagram or your Studio 4 block diagram in here, which are also the top level diagrams. So the thing that is present at the top of your hierarchical design. Now notice over here, we didn't talk about what is inside the control block. We didn't talk about what is inside the multiplexer. We didn't talk about what is inside the register. We didn't talk about anything there. We just laid out the main blocks that make our shift and add multiplier. Of course, we are not jumping into the multiplier itself over here. We are just talking about how we can represent that in a top level diagram over here. So a couple of things that I want to go over. The things that you see in this fashion, they mean that this is just one bit. For some reason I've been using this. All right. So 1 bit here, these are all 1 bit inputs. But when you see something like this, or just that means it's a 4-bit bus. In this case, it's an output of the control block going into the RAM block. Similarly, you will see 32-bit buses in the design. We have been looking at 4 to 5-bit buses for our studios. So that's the thing that I want to talk about. There is not a very good, there's no active low signals in this case. So we'll talk about active low and active high in the next example. Other documentation standards include output from a simulator. So we can actually use Vivado to generate a simulation output. That output, a timing diagram, could be another documentation standard we could talk about. And then specialized timing diagram drawing tools. We will take a look at this in LogicWorks when we come to it. The hardware description language itself, you could have a text-based, syntax-based language there, which is written up as text. And in fact, it can be as big as a book. The reason is you are trying to describe the hardware in a very, very low level. And those kind of details can go on for many, 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 many pages. And the benefit that we have when we use VHDL is simply to say, library use IEEE 1164.all, right? So we are just essentially calling that library, and we don't have to rewrite all those definitions in every file. Now, I want to really get to the signal names and active levels, because this is going to be crucial going forward. You will see a lot of signals, mainly the outputs. Many places you will also see inputs being active low. So the question is, how can we use the signal, how can we write signal names to be very descriptive, right? As soon as you see them, you should know what active low, what signal is active low or active high. So first of all, what is a signal, right? So where do you see a signal? Well, this could be an input or inputs. It could be outputs of your design, or it could also be intermediate signals. I should say intermediate outputs. So we have a classification here in terms of signals, active low and active high. So let's try to define them. What is active low and what is active high? Let's do active high first, because that is something that you guys have been seeing so far. A signal is active when high, or when it is asserted. Inactive when low. No, you don't have to do convolution. These signals are, yes, you don't have to do a convolution. These are digital signals. Let's talk about active low. And this is probably easy to guess. A signal that is active when low, inactive when high. Have you guys seen any active low signals already in your studios? Anodes, okay, what else? Anodes was active low. What else was active low? Segments, yeah, segments was active low. Yes, so segments and anodes. LEDs, I think LEDs were actually active high. The switches were active high. The push buttons are active high. The LEDs I thought were active high as well. But segments and anodes definitely were active low. All right, so let's talk about how do you write them, right? What kind of names, very descriptive names you choose for active low versus active high. So on the left column, you have active low. On the right column, for the same signals, you have an active high version. So I'm just going to point out the differences over here. You guys, I'm sure you can clearly see it. But I'm going to start from all the way at the bottom. Underscore L at the end of the signal name, as opposed to no underscore L. That is the differentiation that you will see the most for active low and active high. There are others as well. So for example, a slash sign at the front, a tilde sign at the front, tilde sign at the end, an asterisk, parentheses L, dot L, a minus sign. So all those are going to suggest that it is an active low signal. On the other hand, we have active high for plus dot h, parentheses h, absence of asterisk, tilde, slash, and underscore L. So all those names are associated for active high. So the moment you see the name itself on a schematic, so for example, error underscore L, then you would know that that error signal is an active low signal, and when it becomes low, that's when you know an error has occurred. So let's talk about that particular concept, and we'll stop with this discussion in a few minutes. Suppose you have a logic circuit that has one output, and I have named that particular output error OK underscore L. Error OK underscore L is an active low signal. Can I say that? Based on active low. So based on how it is written with the underscore L, that's when you know that it is active low. So when it is low, what does that correspond to? And when it is high, what does that correspond to? So you see it's saying error OK underscore L. So when it is low, everything is okay. No error. Everything is okay. And when it is high, that it means error. Now, for the next logic circuit, you have one output, and then that is fed into a NOT gate. You have another output, then you have another NOT gate. So we are essentially changing the active level as we go through these NOT gates. At the beginning, you have error underscore L. What does that mean? That means that low corresponds to error, and high, if that particular output is high, that means no error. No error occurred in some context with that circuit. Now, when you put this through a NOT gate, you see what happens to the symbol. The underscore L cancels out after the NOT gate. And over here, you just have the signal called error. So if it is low, that means no error. And when it is high, it means error. And you can actually put that through a NOT gate again to get a signal that is active low. And we can call that error 1 underscore L. Again, for that one, it'll be similar to this. Low means error, high means no error. So this particular example just describes how you can go from an active low to an active high signal, and how do those names correspond to what they mean. So for example, error underscore L means that if the signal is low, that's active, so error has occurred. And if the signal is high, then there's no error that occurred. All right, let us stop over here